Welcome back to Algorithms and Uncertainty. Today, and also in the following lecture, we will be considering problems of two-stage optimization. What is this all about? Let me start with a very simple example. Namely, you might wanna or you might have to travel to Berlin some months from now. And what are your options? Well, you can either buy a very cheap ticket now, or you can decide to only buy a ticket when you know for sure whether or not you'll have to travel, and then your ticket will be much more expensive. And for simplicity, let's now assume that you actually only have these two choices, and you also know right now what will the probability be that you will have to travel to Berlin. And what you could do now is you could just compare the two expected costs. Namely, the expected cost when you buy the ticket now, this will be definitely 17.90 euros, or when you have a probability P that you travel and you now decide not to buy the ticket, then your expected cost will be P times 115 euros and 80 cents. And now you could just make the distinction depending on the probability P. Of course, this is very simplistic. This is a very simplistic perspective because maybe over time things get more clear to you whether or not you will have to travel. This is something that we're ignoring for today. So we'll only have the two choices of buying things in the first step when there's still uncertainty, and buying things in the second step when there is certainty. But what we're doing is we are moving this to a combinatorial setting. The combinatorial setting we're considering today is set cover. So this is another version of set cover which also includes uncertainty, but the uncertainty is now different from what we know in the context of online set cover. Before we get there, let's first recall the definition of set cover. In offline set cover, we have U. This is the universe of M elements. And we have S, which is a subset of the power set of U, which is, as I was saying, a family of subsets of U. This is the cost of the set S. And our goal is to find a cover. Which is a subset of this family of subsets. And what do we need? We need that the union of all the sets that we have in the cover is our entire universe, and we want to minimize the sum of the costs in the cover. So far, so clear. We've already seen this as an online problem. How did we turn this into an online problem? Well, we had that the universe of elements was revealed one after the other, and as soon as an element arrived, we got to know how it can be covered. Now we're doing something different to introduce uncertainty. Namely, we actually know all of this in advance, but not all elements have to be covered. Not all of U will have to be covered, but instead only a subset of U has to be covered, and this subset is uncertain at the beginning, and we'll now have two stages. First, we don't know what set of elements is active, but then adding sets to the cover is cheaper than in the second stage. In the second stage, we do know which elements are active, but adding sets to the cover is more expensive. But only after the second stage things are evaluated, only after the second stage the set of active elements has to be covered. So in the two-stage version, only A, which is a subset of U, has to be covered. This means that eventually we'll need that the set of all S in C will have to be only A. But, as I was saying, A is uncertain from the beginning, but we know a probability distribution. So, PA, this is the probability that A will be active. And now we'll have two costs for each set. We'll have the first stage, where we can add sets to the cover at cost C1. But we only know these PA, not A. And then A is revealed, and then in the second stage we can add sets to the cover at cost CS2. And at that point, we know A, of course. Good. So how do these C1 and C2 relate? Well, certainly we should have that CS2 is at least CS1, because what we can do in this first stage, we can also always do in the second stage. We have the same sets available, but this only makes sense if these are more expensive. So if those are identical, then we should defer all decisions to the second stage. Or if what could else happen? What else could happen is that the costs of sets are infinite in the second stage. Then we should cover everything in the first stage. So what is important here is that we do know in advance these probabilities that elements will be active. And based on this, we can already choose to add sets to the cover at a cheaper cost. Then the set of active elements is revealed, and then we have to add further sets to the cover, maybe, if A is not covered so far by what we selected. And then but then the costs are of course higher. The costs are then C2. But we have the advantage that we know what we'll have to cover. And the two extreme cases here are that the first stage and the second stage costs are identical. Well, then there's no point in doing anything in the first stage. If the flexible train ticket is exactly as expensive as the non-flexible train ticket, well, there's no point in already now buying a train ticket. But if there is some if it happens that in the second stage you cannot actually buy things, or things are extremely expensive, then you should be prepared for anything that could happen. So how do you capture the train ticket example here? Well, this is actually in my model kind of trivial now, because we have a universe of only one element, and this may be active or may not be active. And we have the option of covering it when we only know a certain probability, or when we actually know whether we are traveling or not. And what's now the overall goal? The overall goal is, of course, to minimize the sum of the costs that we incur. And which sum of the costs? The expected sum of the costs. And let me introduce some notation for this. Namely, and I write here this C0 as the first stage choices. And here I have this CA, which are the second stage choices. When A is the set of active elements. So this is something that you want to convince yourself of, that in the first stage, well, there is no randomness so far, because all you know is actually the probability distributions. You haven't seen any realizations. So what you're doing in the first stage, this shouldn't be random unless you're using some randomization, but let's ignore this for now. And in the second stage, then this is of course a random variable, because this now depends on the set of active elements. Good. So the first thing that we should now do is to discuss, what are we even looking for now? Well, ideally we would like to make the optimal choices here. But what is the best choice that we can make, and what will be our point of comparison? So what's our goal now when we're trying to solve this two-stage stochastic set cover problem? You may realize that this can actually be represented by a Markov decision process with only 2 steps. So the time horizon will be 2. And why is this? You have the first initial state, and then you'll choose as your action, you'll choose what to cover in the first stage, and then you transition to a random state, where you'll now have to keep track of, on the one hand, what you covered, and on the other hand, there's now the random component, which is the set of active elements. And then you'll have to choose another action, namely what to choose in the second stage, and then what you'll have to make sure is that all of the active elements are covered. This sounds very simple, very easy, because the time horizon is only 2, so what's the matter? Well, the matter is we have super many actions and we have super many states. Why do we have so many actions? Because we don't only have one action for every set that we could choose, but we have, so for every single set that we may choose to cover, but we actually have an action for every possible choice of sets in the first stage. And this is why we cannot compute the optimal policy in polynomial time, or at least it's not obvious how to compute the optimal policy in polynomial time. And when you think about this, it's actually not conceivable that you'll be able to compute the optimal policy in polynomial time. Why is that? Because this problem generalizes set cover. Set cover is an NP-hard problem, and if you now, for example, set the first stage cost equal to the second stage cost, and the set of active elements always to your entire universe, then the optimal policy is nothing but the optimal set cover solution. So computing the optimal policy here will be hard. Unless P is equal to NP, you cannot compute the optimal policy in polynomial time. So what is it that we can do? What is it that we can hope for? We can hope to approximate the optimal policy. We can hope to be able to compute a policy which is not much worse than the optimal policy that we have, that exists for this setting, but which we cannot compute. So if we were to write this down formally, we would say now, I'd now like to use the following notation. For any instance I, what do I mean by an instance? I mean the universe of elements, the cost vectors, so the first stage cost, the second stage cost, and also the probability distribution over possible active sets. And for those, we'll define C subscript I of pi as the expected cost of policy pi. And now, of course, we'll have that there is an optimal policy. So this is the policy that minimizes the expected cost for this particular instance. So we know the universe of elements, we know the cost vectors, we know the probability distributions. Among all these, there is one policy that minimizes this expected cost. And our goal will be, given any instance I, we would like to compute a policy pi such that the expected cost of the policy that we compute is at most alpha times the expected cost of this optimal policy, where of course this alpha is as small as possible. Why am I being so slow here? Because I'd like to make clear that we are not doing some kind of competitive analysis. The only thing that we're trying to compute is something that is close to the optimal policy. And this optimal policy, well, is still a policy of the Markov decision process. It is not an offline optimum. This optimal policy that we will also be comparing ourselves to also only knows in the first stage the probability distributions, and only in the second stage it knows the actual realization. You could also picture the same setting where you are comparing yourself to an offline optimum. So this offline optimum, what would that do? That would know in advance the realization of the active elements. And then what would it do? It would certainly cover all elements that it has to cover in the first stage and nothing else. But it's not difficult to see that this is a completely hopeless comparison here. Because it might just be that the first stage is super cheap, whereas the second stage is super expensive, but you wouldn't know what to do without actually knowing the realization. In the lecture notes, you'll find a very simple example that you are actually not able to do anything compared to this very strong offline optimum which knows the realization of the active elements. So instead, we are comparing ourselves to the optimal policy. So to say, this is now an apples to apples comparison, because what we are doing, or what we are able to do, what we know, is exactly what we are comparing ourselves to. But why are we not simply computing the optimal policy? Because that's not possible unless P is equal to NP. Did I really write it this way? That's of course nonsense unless P is equal to NP, or if P is not equal to NP, this is what it should mean. Then we are not able to compute an optimal policy within polynomial time, because this would require us solving the set cover problem. Good. So this is what we'll try to do. We'll try to find a policy which is close enough to the optimal policy of this Markov decision process. And before we get there, let's once again have a closer look at just the offline set cover problem and what kind of approaches one can take there, how one can solve the offline set cover problem, and what is known for that. Before we now get to the two-stage optimization problem, let's first talk about the offline single-stage optimization problem. So everything is known, we just want to cover the entire universe of elements. How do we do that? For this, we've already seen the LP relaxation. Maybe let's first remind ourselves what this LP relaxation looks like. We are minimizing the sum of the CS times XS subject to each element being fractionally covered by at least 1, so the sum of the XS being at least 1 for all elements in the universe. And of course the XS are non-negative. This we've seen before. So rather than now allowing you to only take fractional sets fully or not at all, we now allow you to take sets fractionally. So we allow you to take a set of a fraction of a half, and then another set of a fraction of a third, and maybe a fraction of a sixth, and then overall this gives you 1. This will turn out to be important for designing the two-stage algorithm, but another component which will turn out to be important is the greedy algorithm. How does this work? Initially we set U prime to be all of U, and now we do the following while U prime is not empty. U prime we understand always as the set of elements which haven't been covered so far. Then we let S be the set that minimizes CS divided by S intersect U prime, and then we'll add S to C, and we set U prime to be equal to U prime take away S. This is a very classical approximation algorithm that you might seen also in classes about approximation algorithms. U prime is the set of elements which we have not yet covered. And while there are still elements we not yet have covered, we choose one of the sets to cover them. And this then we add to our cover. And then everything that was inside the set S, of course, gets removed from U prime. And how do we make the decision what to remove from the cover, what to now cover? We take the set that minimizes this ratio. What does this ratio mean? This ratio is the cost of the set divided by the cardinality of S intersect U prime. Recall U prime, those are the elements that we still have to cover. So S intersect U prime, these are exactly the elements which are now newly covered. And what we now ask is, well, which of the sets covers us elements for the minimum cost per newly covered element? So this set might be of different size. If, for example, all costs were identical, then we would simply take the set which covers as many elements as possible for the first time now. And this algorithm you can actually analyze. And for this you can prove the following. If we let C be the cover computed by the greedy algorithm, and X star be an optimal solution to the LP relaxation, then the cost of the cover that we compute is at most O of log m times the objective function value of the optimal LP solution. So maybe you've seen this algorithm just being analyzed to the optimal integral solution. What you can also do is you can also show that this algorithm is an O of log m approximation compared to the best fractional solution. Of course, here what we're doing is we're computing an integral solution. We're computing a real cover. So we don't take sets, we don't take fractions of sets, so only a half or so. But the point of comparison that we're comparing ourselves to, this is allowed even to take a half of a set and a quarter of another set and so on. And still we can show that we are only that our cost is only an O of log m factor higher than this the cost of the optimal fractional solution. Good. So maybe you've seen even the proof of this exact theorem. Maybe you've seen this in comparison to the optimal integral solution. Either way, for completeness, we'll also prove this theorem today. But before getting there, let's first see how we can actually use all of these techniques, all of these building blocks to actually build an algorithm for the two-stage problem, because this is what we are actually interested in. Let's now talk about an algorithm for the two-stage problem. How can we design an algorithm for the two-stage problem? What we'll make use of is the LP relaxation of the single-stage offline problem, where, well, we know everything in advance. What we'll now do first is design an LP relaxation of the two-stage problem. How can we do that? We will now introduce two kinds of variables in our LP, namely we'll have the first stage decision and we'll have the second stage decision. And XS is the fraction of which S is chosen in the first stage, and Y subscript A comma S, this is the fraction of which S is chosen in the second stage, if A is the set of active elements. And now what we'll do is we'll actually write down the same kind of an LP that we have up here. So what are we minimizing? We are minimizing, take the sum over all sets, the first stage cost times access plus what's the probability that the set A is active times the second stage cost. So here we are actually taking the expectation over the set A, and then we're asking what is the second stage cost that we are now incurring. Here this may of course depend on A, this does not depend on A. And what's our constraint? This should now look something like this, and indeed it does. Namely, what will have to happen? The sum of the x's which contain set an element E plus the sum of the y a comma s will have to be at least 1 for all A and for all E in A. And of course, these variables are still non-negative. So the idea of this LP relaxation is just reusing the ideas from the offline LP relaxation. So now we have two kinds of variables. And what do our constraints mean? Or we have only this one kind of a constraint. And this now means that for every realization of the set of active elements, we need that for every element which is active then, that the sum of these fractional values sums up to at least 1. Elements which are not active, for them, of course, this constraint does not have to hold. This is the exact point. The exact point is that only for elements which are active, we have to cover them. And this may happen by our first stage choice. The first stage choice, of course, does not depend on A because we don't know A then. The second stage choice does. And our objective is, of course, to minimize the first stage cost plus the expected second stage cost. And now it's really easy to realize, well, every feasible policy corresponds to a solution to this LP of the exact same objective function value. Every policy pi corresponds to a feasible LP solution x comma y such that the expected cost of the policy is exactly equal to the objective function value. But the other statement that you could picture, namely that every feasible LP solution corresponds to a policy of the exact same objective function value, this is not true. Why that? Because policies may only choose a set entirely or not at all. They may not say, okay, and I choose this set for like a fraction of a half of this set and a fraction of a half of that set. And this is exactly what we observed earlier, even for the offline problem, for the single stage problem. there are fractional LP solutions which do not correspond to integral LP solutions. But what we can now do is we can still turn fractional LP solutions into integral ones. We've seen this in the case of online set cover, that we had this fancy randomized rounding algorithm there. And in a similar way, but actually in a much easier way, we can do this now by relying on the greedy algorithm. So our algorithm for the two-stage problem is as follows. We compute an optimal solution to the LP relaxation, which we want to call now X star Y star. And what do we do now? U0, we call all elements in the universe for which the sum of the X as star is at least a half. And now we compute the first stage cover. Recall that we called this C subscript 0. By running the greedy algorithm on the universe U0 with costs CS. This is what we're doing in the first stage, and we'll compute the second stage cost, the second stage cover, by again running the greedy algorithm on A takeaway U0, and now our costs will be CS2. So how does the algorithm work? Well, we'll compute an optimal solution to our LP relaxation. And this LP relaxation becomes now important to define the set U0. And how is this defined? It consists of all the elements for which the fractional LP solution decides to cover them by at least a half already in the first stage. And these are exactly the elements that we are now covering ourselves in the first stage. And then in the second stage, we'll just cover the rest. There's actually not much choice that we have. Okay, U0 is already covered, and then we'll cover A takeaway U0. And how do we decide what to cover? In both cases, we run the greedy algorithm. You could also do this in different ways. You could also use other approximation algorithms, but for concreteness, let's now talk about just running the greedy algorithm, for which we have this property that the sum of the costs in the cover that it computes is an O of log m approximation to the optimal fractional LP solution. This is what will be important. There's one thing you might ask here is, how are we even able to compute the optimal solution to the LP? And this is indeed an important question. If we go back to the LP, then we are saying here, okay, take any subset A of U, and subsets, there might be exponentially many subsets A of U. And for simplicity, we are now assuming that, well, there are only polynomially many sets A for which PA is actually greater than 0, because then there are only like polynomially many scenarios, only polynomially many possible active sets that we're considering here. And then this LP is kind of small, and we can just assume that we are able to compute the optimal solution in polynomial time. Also, when this is not true, then there are a couple of things that you can do, but then actually things get much more messy, much more technical, much more difficult, because then you'll have to talk about how do you even solve LPs. So therefore, let's only talk about the case that there are not too many PA which are greater than 0, or let's just assume that we're able to execute this step here, that we're in polynomial time or within reasonable time, we're able to compute an optimal solution to this LP relaxation. Because what I want to talk about now is why does this approach give us a good policy? And what we'll now be able to show is the following. We'll be able to show that the computed policy is an O of log m approximation to the optimal policy. And what does this mean? What do we want to prove? So we claim that the sum of the costs that we have for our first stage choices plus the expected sum, the expected cost that we have for the second stage choices, this is no more than O of log m times, and now we'll write down the expected, the cost of the optimal LP solution. So this was CS1 times XS star plus sum of all A, PA times the sum of all S, CS2 times Y, SA star. So if we're able to show this inequality, then we are done. Because, why is this? We know that the optimal policy has at least this cost, and this is exactly what what is the cost of our solution, of our policy that we're computing. And what I'd like to talk about first is what is this? What is the first stage cost of our algorithm? How did we get to our first stage decision? Let's go back to the algorithm. We take the set U0 and then we run the greedy algorithm on U0. So what does this mean? On the set U0, C0 is the solution of greedy computed on the set of elements being U0 and the costs being the first stage costs. The LP relaxation of this is the following. We would want to minimize the sum of the first stage costs subject to all elements being covered, but now we say, okay, only the elements in U0 have to be covered. And of course the x's have to be non-negative. We know that this C0 that the greedy algorithm is computing is only an O of log m factor more expensive than the optimal solution to this linear program. But what is the optimal solution to this linear program? Well, we don't know. But where did the set U0 come from? Let's go back. U0 was the set of all elements which are covered fractionally by x star by at least a half. So this means that 2 times x star is a feasible solution to this LP. And this means that what our algorithm, or greedy algorithm, is computing here will be at most an O of log m factor more expensive than the optimal LP solution to this. But the optimal LP solution to this LP will definitely be only cheaper than if we plug in here 2 times x star, which is a feasible solution to this LP. Good, so this already bounds this first part by, in fact, this time, this part here. Cool. Now we'll only have to bound this here. Or more precisely, let's talk about this part here. So how expensive is the second stage? So CA this will be the solution by the greedy algorithm on, and now take A take away union A take away U0, and the costs will be CS2. And what's now the matter? Let's consider such an element in A take away U0. What do we have for that? We'll have that the XS star plus the YSA star, they will have to sum up to at least 1 because we have a feasible LP solution. But what do we know about this here? Well, this is not in U0. So E is in A take away U0. So this will have to be less than a half, which means that this other part here will have to be more than a half, or at least a half. Which means now that 2 times y SA for the different s is now an optimal is now a feasible solution to the LP which we use to solve to compute what we're doing here in the second stage, just exactly like we had this up here. And so this now means that the cost that we incur by the sets of the second stage, this is at most O of log m times, take the sum of all sets, CS2 times 2 times y SA star. And if you now do the math, or if you just have a closer look at what we did, then you'll see, okay, this part here is now actually bounded by O of log m times this part here. So overall, we'll have that the first stage cost we're incurring is at most O of log m times what the LP is putting on the first stage. The second stage cost that we have is at most O of log m times the second stage cost, and this holds even for any set of A of active elements, even for every possible scenario individually, this is true. So this together shows the claim. And this way we've already proved this theorem. Good. So I think this is surprisingly simple once you know how to write this down as an LP, because what you'll see is in this set cover problem, with a fractional LP solution, everything gets covered at least by a half in the first stage, or at least by a half in the second stage. And what we now do is we actually take this apart and we'll now say, okay, we either cover you fully or not at all in the first stage, or we do the same thing for the second stage. This is an approach that you can generally hope to also use for other problems. What of course now is happening here is that all the magic is eventually hidden inside the LP. To be honest, there's nothing really smart that we have to do anymore, because we already have the feasible LP solution. And this is something maybe you should generally keep in mind, that if you want to find a good policy, then maybe you should just write this down as an LP and then hope that the LP solution already tells you what to do. Cool. So what we still like to do, of course, is to understand why does the greedy algorithm have the property that we claim it has. Namely, we now use this twice. We use this here, that the greedy algorithm has the property that if we run the greedy algorithm, that the solution that we compute is only an O of log m factor more expensive than the optimal LP solution. We use this up here and we use this down here. What I actually find interesting there is that the greedy algorithm doesn't actually solve the LP. The greedy algorithm only well, is the greedy algorithm. It's that simple. But as it turns out, the solution will not be much more expensive than any LP solution, so in particular not much more expensive than the optimal of these LP solutions. So this is what we still have to do to complete the picture of this algorithm, to complete this analysis, namely, why do this and this step actually hold? What we still have to do is to analyze this greedy algorithm. How did this work? Well, we at all times maintain the set U prime of elements which still have to be covered. And while there are still elements which have to be covered, we'll choose a set S which minimizes the cost divided by the number of elements that are newly covered, and then we'll add this set S to our cover, and of course we'll remain everything that is inside S from the cover. And this, the solution that we compute this way, the cover that we compute this way, we want to compare to the optimal LP solution, or in fact to any LP solution of this fractional relaxation of set cover. Before we do this, let's introduce some more notation. We let EK be the kth element to be removed from U prime. And what does this mean? Well, we now remove, of course, elements from U prime because we are covering them. And usually we will be covering multiple elements at a time. But we now say we bring them into any order, so we want to break ties arbitrarily here. So in the first iteration, maybe not only E1 is covered, but maybe also E2, E3, and so on. So a couple of elements might be covered in the first iteration. And so actually all of them can be considered the first element to be covered, but we bring them into any order. And furthermore, we have the following notation. We let Sk be the set that covers Ek for the first time. Of course, any element might get covered multiple times here because we're not actually talking about what happens outside of U prime. Well, then the element might not be contained anymore in U prime, but it might get covered another time just because it so happens that other elements get covered this way. But this is what we ignore here. We just say that Sk is the set that covers Ek for the first time. So this is the set that we're picking in the iteration in which Ek is being removed from U prime. And we also let Uk prime be the state of U prime before the iteration in which Ek gets removed from this set. So before Ek is covered. Good. And now we also define something that was very important, namely, we'll define how expensive is it to cover element Ek. And for this, we'll define the price of element K, or element Ek. So this is the kth element which is covered. And how did we choose what to cover? We chose the set that minimizes this ratio here. And let's now say that pk is this ratio for this element. And now what is crucial is that the sum of the costs that our algorithm incurs is exactly the sum of these pk. Why is this? Because here we're exactly splitting up the costs of CS over the elements that are newly covered. And for all of them, we have this same ratio here. And we are now, if we're adding up these, we're actually nothing but adding up the respective CS for the sets S that we are picking. So all we have to do is actually bound this sum of the pk. And what we now claim is the following. We claim that for all k, pk is no larger than the following. Take the optimal LP solution and divide its objective function value by m minus k plus 1. So this means that we can upper bound this ratio at the point where the kth element gets removed, namely by this much. For example, when the first element gets removed, then k is equal to 1, then the cost for covering the first element is no more than the optimal LP solution value divided by m. And why is this true? We certainly have that pk is at most CS divided by S intersect UK prime for every set S. Why is this? Because the set SK that we're choosing is actually the one that minimizes this ratio. And this now lets us do the following. It's now just some magic of rewriting these things. Take the optimal LP solution. The optimal LP solution's value is at least what we would get if we were only considering the sets which have a non-empty intersection with UK prime. And now for these, so initially just think of UK prime as being the entire universe, so then nothing is happening here. And now we can split this up, or we can just rewrite this as follows. Should be non-empty. We take the optimal LP, we take CS times XS star, and we divide it by S intersect UK prime, and then we multiply it again with S intersect UK prime, and of course. And maybe it's even easier if we move this XS star that we had here back here, because then this looks familiar then suddenly. So there's nothing actually happening here except for the fact that now here this is at most, at least this here, this is at least pk. Why is this? Exactly because of this inequality here. And what do we have regarding the rest? So this is at least pk. Now what do we have for the other sum? We have that take the set over all S, S intersect uk prime times x star. Now how much is this? We can play around with that. Namely, what we can do is instead take the sum over all elements here rather than taking the cardinality here. And now what we'll have to do is just to swap the sums. And now, that's interesting what we're seeing here. We're seeing for the sum over all elements in UK prime, and for each of the elements we seeing how do these x s star add up. But this here, this will always be at least 1, so this will all together be at least the cardinality of UK prime. So if we combine this, then let me now continue in black for where we are here. We'll see that we immediately see that this is at least pk times the cardinality of UK prime. And what does this tell us? This tells us that pk is no more than the optimal objective function value divided by the cardinality of UK prime. And what's the cardinality of UK prime? The cardinality of UK prime, this is the number of elements that are not covered before the kth element is covered. Now this, you might say, okay, the number of elements that are covered, so this is the number of elements that which are not covered so far. You might say that the number of elements that are covered is k minus 1. Well, it might even be fewer than k minus 1. This is why this is at least m minus k minus 1. Because it might be that some elements get covered simultaneously. So this is m minus k plus 1. And, oh, that's great. This proves exactly this claim. And now, all we have to do is actually we'll have to take the sum of these pk. So to prove our theorem, we now use that on the cost of the sets that we choose in our cover is at most, as I was saying, the sum of these pk, or this is actually even equality that we have here. And now each of these pk we can upper bound by cs times xs star divided by m minus k plus 1. And so what we're getting here is actually the sum of the cs times xs star, and that we multiply with the sum of the 1 over m minus k plus 1. And this here, this is nothing but the mth harmonic number, which is in the order of log m. Good. So this was our analysis of the greedy algorithm. It is a little messy down here, and I'm still trying to figure out the best way to actually do this argument. Eventually what you're doing here is nothing but to realize that you have a feasible LP solution, and this is why there has to be a set which is cheap in this sense, because otherwise, if all sets were expensive, then the LP solution couldn't be this cheap. This is the general thought that you should have when you are proving this. At the same time, I feel this is a bit technical happening down here, but eventually all we care about is that this gives us this O of log m approximation compared to the optimal LP solution. And that's interesting. Here we get something compared to the optimal LP solution, although we don't actually know the optimal LP solution, and we don't care. And this is just maybe surprising at first sight, but then again, it's not so surprising when you realize, okay, this is actually what you usually do when you design approximation algorithms, that you compute something which is good compared to something which you don't actually know. And why did we care about all of this? We cared about all of this because we used this greedy algorithm twice in our algorithm for two-stage set cover. And in the two-stage set cover, we indeed used the fact that we were good also compared to the best fractional solution. And there, this comparison to the best integral solution for the set U0, for example, this isn't clear how to do. Maybe you cannot do this at all. Doing this via the LP relaxation, this was extremely straightforward. Good. So this concludes our lecture for today. We've seen this approach of designing algorithms for the two-stage problem via the LPs, which you can also use for other problems. This is generally a very simple technique as long as you just don't question too much that you can solve this LP in polynomial time. Next time we'll consider a different approach to two-stage optimization, where we're not actually using an LP relaxation, but we also don't need only this polynomial support or that small support of the probability distribution. So we were assuming today that there are only these few scenarios. This is what we won't assume. And we'll see another very nice, clean technique to design algorithms for this two-stage problem. Until then, please do let me know if you have any questions. Stay safe. Bye.